You're all joining me for a video here on determination of a specific area, whether it's finite or infinite. I am Mr. Ish and thank you for joining me for this video. We have this integral over here, 2 integral dx divided by x squared plus 9 from minus infinity to infinity. If you were to look at it in terms of a function, that's exactly what you're looking at. If you were to zero out this x, you're really looking at a 2 over 9 in terms of a y-intercept. If you were to graph it out, you would look at something which would look like this. You're looking at it from minus infinity and you're looking at it up to positive infinity. All of this area right here is being examined and you have to determine if that's finite or infinite. Well, that's a question we have at hand. We can do this integral here by two means, trigonometric substitution or utilize the arctan antiderivative. You know which one is the easier option and normally you should lean towards the easier option. But because this is a video, I should do both options. But generally, the arctan antiderivative has this format. As you know, you're looking at something which looks like a 1 over a, and then you have an arctan x over a plus c. But we're not doing the plus c because we have a definite integral. That would be the template you would utilize for this. But simply because we have a 2 over here, it would come right over here. If a squared is equal to 9, a is equal to 3, you would just plug that in. You'd have a 2 over 3. You'd have an arctan x over 3 plus c, but you would really be looking at it now from infinity up to minus infinity. That's exactly how your arctan antiderivative would come, this template. It's very easy. You know, I've produced a video on this template, how it comes about and why it's so beneficial. Anyhow, when you're looking at the arctan, the graph of an arctan, you know you have two asymptotes horizontal. You have a pi over 2, y equals pi over 2 and a minus pi over 2, and it always goes to the origin. It shoots up like this, then it goes across. It shoots down, then it goes across. As this function proceeds in the direction of infinity, it proceeds and approaches pi over 2. In the direction of minus infinity, it approaches minus pi over 2, and you can utilize that to your advantage. Put 2 or 3 out and you're looking at basically arctan. When you're doing an minus infinity divided by 3, because infinity here is coming in places of x, infinity divided by 3 minus infinity divided by 3, that over 3 becomes meaningless. You're really looking at this right over here, and you know there's nothing wrong with you looking at it in this way. But when you utilize a graph, and you could utilize a calculator, when you utilize a graph, as the arctan function approaches infinity, you're hitting pi over 2. As the arctan approaches minus infinity, you're hitting minus pi over 2, and then you have a 2 over 3 sitting out here. Pi over 2 plus pi over 2 is a pi. Pi times 2 over 3. Well, the area below the curve is a very good finite number, and it comes out to be 2 pi over 3. So is this integral here looking at a finite or an infinite situation? Well, it's looking at a finite situation, and there it is. It's 2 pi over 3. But you know, this right here, utilizing the graph, you could have utilized the calculator. You can do an exceedingly large number like 1 exponent 99, and you can inverse tan it. You'd get a 90 degrees. Pi over 2, you could do 1 in exponent 99. You see I have a negative number, and you can do inverse tan, you'll have a minus pi over 2. So it very well corroborates the graph, very well corroborates a calculator value. But this right here is utilizing the arctan antiderivative. If you are unaware of the arctan antiderivative, then you are stuck with utilizing the trigonometric approach, but the trigonometric approach should yield you the same result. And remember, when you're looking at this, you know what you're really looking at. You're looking at a type 1 improper integral because you have infinite intervals or limits which are at infinity. You know here a is equal to 3 because a squared is equal to 9, a is equal to 3, x is equal to 3 tan theta. We're really looking here at a trigonometric substitution which involves this type of a format, which brings in the tan and the secant items in terms of the substitution. X is equal to 3 tan theta, dx is equal to 3 secant squared theta d theta. Now how do we determine the new limits? Theta 1 and theta 2, everything here is with regards to this right here, but everything here is with regards to these values here, because you're really looking at a minus infinity and a positive infinity. If you put minus infinity over here, you're doing again minus infinity inverse tan, you'll get a minus pi over 2, and you can do that with your calculator. Minus infinity of exceedingly large negative number, inverse tan it, you get a minus pi over 2. You put infinity here in place of x divided by 3, it's still infinity, inverse tan, you get a pi over 2. So now suddenly everything here becomes this in terms of your new definite integral. That's exactly what it is. A type 1 improper integral has become a very proper integral, which is why we're seeing convergence in this. Anyhow, dx is 3 secant squared theta d theta, and then right here x squared plus 9. That would be a 9 tan squared theta plus 9. You have a 2 out here, you have a pi over 2 minus pi over 2. Clean out this area. You're isolating a 9 and you're bringing a tan squared theta plus 1, which is really a 9 with a secant squared theta. If you were to clean it out, the secant squared thetas would cancel. You have a 3 here and you have a 9 over here, which would become a 1 over 3. That 1 over 3 can be pushed out as a 2 over 3 because you already have a 2 sitting out. Remember again, this became a secant squared theta. This secant squared theta cancels out with that. You have a 3 which cancels out with this 9 and brings in a 3. A 1 over 3 comes out as a coefficient that attaches to 2 over 3, and you end up having nothing here other than d theta. When you're looking here now, the antiderivative of this is basically 2 over 3 theta. And you're looking at it from pi over 2 to minus pi over 2. You do the difference of the 2, you're going to get a pi which will attach to 2 over 3, you'll have a 2 pi over 3. So we're really looking here at a very good convergence of this function right here. And it's convergent because you have a development here of a finite value, and on both sides with regards to the infinity, the limit does exist, and you know the limit exists. Limit as x approached minus infinity, in terms of what I was showing you with the graph, everything approached. If you were looking at the graph of this, I showed you that at the very beginning. We didn't talk about the limits, but I showed it to you. You're looking at something like this. Limit as x approaches minus infinity, this function will approach your x-axis, which is y equals 0. Limit as x approaches infinity, positive side, your function will again approach y equals 0, your x-axis, and there it is. The limits exist at infinity and minus infinity. Remember, I'm not talking about the arctan graph, the function graph. I'm talking about this. For this specific function right here, as x approaches infinity and minus infinity, the function, the limit exists, because if you're looking here and you put minus infinity and positive infinity in here, you're putting such a large number here in the denominator, the entire value zeroes out. I'm not saying you develop a vertical asymptote, but I'm saying all of this becomes equal to a 0 at minus infinity and infinity. So the limits exist on both sides. Hence the type 1 improper integral with convergence and a good finite area developing using the arctan antiderivative and utilizing the trigonometric substitution route. But that right there is the essence of this video. I hope you enjoyed it. Have a great night. Bye.